Hi again. Today I want to look at something called the equilibrium law. Let's start by looking at an example between the reaction between hydrogen and iodide to produce hydrogen iodide. I've made a sketch of how the concentrations would change over time. You'll notice that I put in the dotted line, and to the right of that dotted line indicates when we've reached equilibrium. So I'm going to start talking about that situation when the reaction has reached equilibrium. At equilibrium, we know the rate of the forward reaction equals the rate of the reverse reaction. And from unit number 6 on rates of reaction, I've written the rate law expression for both of them. So in the forward direction, the rate of the reaction in the forward direction is some constant times the concentration of hydrogen times the concentration of iodide. In the reverse direction, the rate of the reaction is a constant, the rate constant for the reverse reaction, times the concentration of hydrogen iodide to some exponent. And here I'm going to choose 2 because that's the coefficient for the hydrogen iodide. I'm now going to isolate these constants, put the rate constants on one side of the expression and the concentrations on the other side. And what you've seen here is that because K forward and K in reverse are constants, they can be grouped together to be one constant. And this is called the equilibrium constant. At any given temperature, the ratio of products over reactants raised to their molar concentrations is a constant value. And that constant value depends on temperature only. So every time you change the temperature, you change the value of that constant. The C is put in there to represent the fact that you use concentrations, molar concentrations. So whenever making this expression up, make sure you're using moles per liter or moles per decimeter cubed. Let's begin writing a few expressions for these for practice. So if I want to write the equilibrium constant expression for the first equation, I put the product, the phosphorus pentachloride on top, and the reactants on the bottom. In my second example, same thing, product on the top, reactants on the bottom. Be careful when you're writing for ions that you make sure that you include the ionic charge because ions are not the same species without the charge. In my last example, the production of ammonia, again, the ammonia goes on the top and the nitrogen and the hydrogen on the bottom, but make sure that you incorporate the coefficients. So notice the 2 has become the exponent for the ammonia and 3 the exponent for the hydrogen. Now there is a small exception to this rule of products over reactants, and that has to deal with the presence of water. If we have a reaction that takes place in an aqueous solution, and water is either a product or a reactant, we tend to leave it out. Now let's look at why that's the case. So I'm going to use the example that's shown below. So as this reaction proceeds, my 2 reactants would be used up. So the amount of them would decrease, as well as their concentrations would decrease over time. The first product that's mentioned there before the water, its amount and its concentration would also increase over time. But the water, on the other hand, its amount would increase, but its concentration would remain constant. And since it's constant, there's no need to put it in the expression as its value never changes. So as a result, when we write out equilibrium expressions where water is present in an aqueous solution, we leave it out. Let's look at a few other manipulations with this equilibrium expression. So here I have 3 related reactions. In the first one, I've measured the equilibrium constant, and it comes out to a value of 49. I'd like to know what the equilibrium constant is for the second reaction. First, I'll write out the equilibrium expression for it, and you'll see that it's just the inverse of the one above. So as a result, the equilibrium constant for that reaction will just be the inverse of 49. If I look at my third reaction and write out its equilibrium expression and compare it with my second one, I can see the difference between these 2 is simply the square root. I've taken the square root of the expression in number 2. And as a result, I just need to take the square root of the equilibrium constant. The equilibrium constant usually is not expressed with units because every time you have a different exponent, the units of the expression would change. So as a result, it's usually standard practice to leave the units out of the expression, but just make sure that you put everything in moles per liter or moles per decimeter cubed. The size of the equilibrium constant also tells us something about the reaction. So if the equilibrium constant happens to be a value bigger than 1, then we know that we have a lot of product and very small amount of reactant. So if we consider the reaction, what would happen is the reactants would proceed to products. We'd make a lot of products and the reactants would almost be completely gone, and it would generate a graph similar to the one shown below. Conversely, if Kc is a rather small number, then I know the inverses hold true. I make very little product. Most of my chemicals stay as reactant. As a result, a lot of reactant, very little product, and the graph would take the shape as I've shown here. I want to introduce something called the reaction quotient for a moment. Now, the equilibrium constant usually refers to the ratio of products over reactants at equilibrium. Q, the reaction quotient, refers to products over reactants at any time. So it could be at equilibrium or even before equilibrium is reached. We use this calculation to determine how close a reaction is to reaching equilibrium. So I'll give you an example of how that might work. Suppose that you're measuring the concentration of hydrogen and hydrogen iodide during the reaction, and you get the values that are shown below. Has this system reached equilibrium? Well, we do some research and we find out that from a literature value, the equilibrium constant at the temperature we're studying, it should be 49. So what we're going to do is calculate the ratio of products over reactants to the appropriate exponents and see what we get. But we can't call it K at this point because we don't know it's at equilibrium. So we use the symbol Q. So substituting in the values in my question, I get 36. So the first thing that I notice is it doesn't equal a constant, so I know that I've not reached equilibrium. But equally importantly, I can also realize what direction the reaction needs to proceed to get to equilibrium. Since my value 36 is smaller than the 49, I need more product, and I need to make the reactant smaller. So that would only happen if the reaction was to proceed in the forward direction. So generally speaking, if I get a Q smaller than K, I need to proceed in the forward direction. Conversely, if the value Q had been larger than the equilibrium constant, my reaction would need to proceed in the reverse direction. So I hope you find that useful. And again, comments are always welcome.